Hey everybody, it's Mr. Carr again. Today we're going to be looking at 1.2 day one. We're going to continue with our equations. In this case, we're going to look at very specifically functions and what our definitions of functions are, and then some special characteristics of them. So let's start with the idea of what is a relation. A relation is a mapping, which is a pairing of input values and with output values. The input values, the set is called the domain, which is typically X. It doesn't always have to be depending on context, but it's usually the X's. Range is the all the possible output values, which is again usually Y, but doesn't have to be. So we can show our functions in a variety of ways. So we can, or sorry, I'm getting ahead of myself. We can show our relations in a variety of ways. So we start here with an or set of order pairs. Okay, my inputs are all the X values here. My outputs are all the Y values. So we can throw them into a table if we wanted to. So we have -2 to -3, -1 to 1, 1 to 3, 2 to -2, and 3 to 1. Okay, we can plot them on a graph. So these are just plotting points in this case. So we got -2 to -3, -1 to 1, 1, 1, 2, 3, 1, 2, -2, and then 1, 2, 3, 1. So they're just points on a graph then. We can also do, sorry about that. We can also do as a mapping diagram. This is where we list all of our inputs. So we can do -2, -1, 1, 2, and 3. We put all of our outputs. Doesn't have to be in the same order, but we can just do that to make it easier. -3, 1, 3, -2. Oh, I don't have to repeat 1. You don't have to list. If a number is repeated, we don't have to write them twice. So -2 goes to -3, -1 to 1, 1 to 3, 2 to -2, and 3 goes to 1 as well. So we're just connecting dots to everything that matches up between the inputs and outputs like that. We can get more specific with our relations. One is a special type of relation is called a function. This is where every input is paired with exactly one output. Okay, so what that means is every input, like inputs cannot be repeated. I cannot have, for example, down here. Well, we'll see it when we get to that. But every input can only go to one specific output. So down here, identify the domain and range of the relation, then determine the relation as a function. So in this case here, I'll write domain. I'm going to use this as my set notation. In this case, domain is all the X values. So I'm just going to write them out as a list. So -3, -1, 2, and 4. Yeah, let me write that a little bit better. There we go. Okay, the range is going to be the same way. I'm going to go with all my Y values. So 2, 3, -4, and 4. 2, 3, -4, and 4. If we look at this, every single input only goes to one output, -3, -1, 2, 4. There's no scenario where, like, let's say 4 went to both 2 and 3. That would not be a function then. Okay, so this one is a function. Yes, just say yes, it's a function. Want to go to the next one? My domain here, got 1, 0, -5, and it's 1 again, so I don't need to write it again. So I'm just going to skip that one. Range is going to be -4, 2, -4 again, and 3. This is where we start seeing a not a function. Okay, since 1 goes to -4 and 1 goes to 3, we are repeating the input of 1. This is not a function. Okay, and my reasoning is that 1 is mapped to both so let me do it this way. Like 1 is mapped to -4 and 1 is mapped to 3. So we can't have one thing going to one input going to two outputs. Same thing happens in the next example here. My domain is -2, 1, and 4. My range here is -4, -1, 2, and 3. We have this right here where 1 in the input is going to two different outputs. That is not a function. Just for comparison, I want to go back a little bit. This right here is a function. We are allowed to take two inputs and go to the same output. That's okay. We are allowed to repeat our outputs, but we cannot repeat inputs. That's the key part there. If we have a graph of a function, to tell if the graph is representing a function, we use what's called the vertical line test. So if you can draw a vertical line anywhere on a graph that intersects the graph more than once, it is not a function. In other words, to be a function, vertical line must only intersect a graph, must only intersect a graph. One second. Sorry about that. So in other words, to be a function, vertical line must only intersect a graph only once. Okay. So we apply our vertical line test to determine the graph represents a function. One thing that I like to do with this, especially if I have my technology here, I will take this and I will just literally drag it across. And you can see that my vertical line only ever hits this graph one time. It's every single time it intersects, it's only one point at a time. So this is, yes, a function. Okay. When I take it here and, oh, look at that. We're crossing, like here, we're crossing a bunch of times. So all it takes is one example here like this. So we are crossing here and here. So it's not a function. And then when I take it further and take it over here, same thing. We've crossed here now. One, two, three times like that. Not a function. Okay. This is another way of showing that one input went to multiple outputs. So that's another way of saying it's not a function. Here's a linear function. It can be written in the form y equals mx plus b. So if you remember from the past, m is our slope, which is a rise over run. B, which in this case is -1, tells me I'm crossing at the point 0, -1. So I would plot my first point here. Rise over run is -2 over 1, so I can go up to the left one, down to the right one, and so on. I could just do a couple more if I wanted to. Okay, so there's my linear function. So it's still a linear function when it's in this format like this, but additionally, we can use function notation like this. Since it's a linear function, we can say it's f of x equals -2x minus 1. So we say f of x. So basically what we're doing is just replacing the y value is all we're doing there. Okay, so next step we want to do is look at determine if the function is linear. To be a linear function, we have to have a slope. We have to have it in this format. And that's just m times x then. So when I look at these, this one is linear. This one is nonlinear. And the reason it's nonlinear is because it's x squared like that. Okay, so that means I can, oh, now my next step is to just evaluate what is g of -4. So I'm going to use my inputs and plug them in like this. Every x value gets replaced. And you know what? Let me go back on that because usually what I do is I like to start with open blank parentheses like this. Okay, same thing over here. So I'm going to do g of blank is equal to 5 times blank plus 8. Now I go back and then I'll fill in all my inputs. So in this case, it'll be -4 in there, and -4 can go here and here. Now let's just do order of operations. So I run through here. I'm going to do my exponents. So g of -4 is going to equal to, this will be -4 times itself is 16. And the opposite of that is -16. Then I could do multiplication. That's -2 times -4 is a +8. And then plus 7. So g of -4 comes out to -16 plus 8 plus 7, which is a -1 when I put them together. G of -4 over here, I've got 5 times the -4 is a -20 plus 8. So g of -4 is a -12. Okay, so let's talk about slope. Slope represents the rate of change of a line, which is telling us the steepness. Okay, so we're telling us how much is it changing by. So I already said this before, it's rise over run. Rise over run is known as change in y over change in x. We can find that with our slope formula, which is y1 minus y2 over x1 minus x2. Okay, so it's this idea, how far up and how far over does it go? We get 4 possibilities here. We could have a positive slope that's going up and to the right when I go left to right like that. We can go down into the right when it's decreasing like that, or a negative slope. Or we can have zero slope, which is a horizontal line, or undefined slope, which is a vertical line. Got a little extra graphics there if you want to look at that for help. So what's the slope of the ramp here? Our ramp is going to be rise over run. So my slope is going to be, if I look at it's 15 inches up, 54 inches across, then I can do that as a rise of 15 over a run of 54. We'd like to reduce that. So if I divide both of these by 3, my slope is 5 over 18. Okay, for the next one, we're going to use the actual slope formula. So I can call it x1, y1, x2, y2. So its slope is going to be y1 minus y2 over x1 minus x2. So when I do that, in this case, it's going to be 3 minus a -1 over -1 minus 2. This will turn into addition. So it'll be 3 plus 1 is 4 over a -3. So it's a -4/3 for my slope. Without graphing, if the line connected is increasing, decreasing, horizontal, vertical, it is a negative slope, so it is a decreasing line. Okay, so that's my proof there. Some other facts about our slopes. Parallel lines have the same slope. So if I have like slope 1, we'll call it, is 2/3. Slope 2 is 2/3. Perpendicular lines, meaning they cross at right angles, they have slopes that are opposite reciprocals of each other. Meaning, if my slope 1 is 2/3, my slope 2 is -3/2. So reciprocal, remember, is flipping the fraction over. So 2/3 becomes 3/2, but one has to be positive, one has to be negative. So we look at stuff like this. Are the lines parallel, perpendicular, or neither? So real quick here, 1 versus -1. So that is 1 over 1, and that is technically like a -1 over 1. So this is perpendicular. They are opposite reciprocals. 1/2 versus 2, they are reciprocals, but they're not opposite reciprocals. So this is neither. Are the lines that contain the following points parallel, perpendicular, or neither? So we're going to find two different slopes. So we'll find slope 1 for line 1 here. That is going to be -1 minus 2 over 0 minus a -2. That is going to be -3 over 2 here. For slope 2, that's going to equal to 3 minus a -1 over 2 minus a -4. So that turns into addition is a positive 4. That also is addition, so that's a positive 6, which reduces to 2/3. -3 over 2 versus 2/3, those are opposite reciprocals. So these are perpendicular. Okay. In real life, slope is again, I used this one earlier, it's a rate of change, which compares the change in one quantity to the change in another. So with slope, that is a constant rate of change. It's the same rate of change the whole time. So if we look at this diagram, we can use this as what's called an average rate of change to kind of describe the growth of the giant sequoia. Okay. So if we look at this in 1965 to 2005, went from 137 to 141 inches. Okay. So when we do the average rate of change for the trunk here, we're going to look at how much did it grow over the years. So it went from 137 to 141 inches. So we're going to do that as like a y2 and an x2, y1 and x1. So we're going to do 141 minus 137 over 2005 minus 1965. Okay, so that changes 141 minus 137 is going to be 4 inches over 40 years, or 1/10 of an inch per year. As a rate of change, it's 1/10 inches per year. So we can use that information to make our prediction for the year 2065. We know that that is 60 more years than 2005. So if we take 60 years, multiplied by 1/10 inch per year, that should come out to a 6-inch difference from 2005 to 2065. Well, because we know that's 141 inches here, let's take that 141 inches and add the 6 inches now to get to a prediction of 147 inches in the year 2065. Okay. And that is it for 1.2 day one. So again, we looked at our functions, a little bit of relations and how that related to each other, as well as our slopes and rates of change of linear functions. All right. That's it. Take care.